Students, in this section we are going to learn the problems or numericals related to the frequency mapping. So let's look at the very first numerical that will guide you related to the concept of quantization. So let's see the statement. Determine the bit rate and the resolution in the sampling of a seismic signal with dynamic range of 1 volt if the sampling rate is fs equal to 20 samples per second and we use an 8-bit ADC. What is the maximum frequency that can be present in the resulting digital seismic signal? So if you just look at the overall statement over here, in this particular statement we need to obtain few things like determine the bit rate and the resolution in the sampling of a seismic signal, as well as it is asked to find out the maximum frequency that can be present in the resulting digital seismic signal. Now, as it is quite clear that fs is given to us, and if the fs is given for the folding frequency f fold, the formula is nothing but fs by 2. So from this particular sampling frequency itself we can just obtain the frequency that is nothing but the f fold. So this is nothing but the f fold, which can be easily calculated from this example with the help of this fs by 2 expression. So 10 hertz is simply calculated over here itself. Now the question is about the resolution. For getting the resolution, if you just able to recall, the formula is x max minus x min divided by 2 raised to b. B means number of bits used for the ADC. So in our case it is given that it is 8 bit. So 2 raised to 8 minus 1. So that is how this resolution can be easily obtained with the help of the given data. So this dynamic range, it means it is nothing but actually the value x max minus x min. So this is nothing but actually that value x max minus x min. It means that if someone says that this is what the sinusoidal waveform, so this is what the x max and this is, let's say, the x min. So in between this is nothing but the dynamic range. So that is what specified here, 1 volt. Now the next part which we need to concentrate, that is nothing but the bit rate. So to get the bit rate, that is capital R. So this is what the formula we need to proceed. So for the bit rate, it is quite easier that we are having the data fs is equal to 20 samples per second and 8-bit ADC is given. So simply multiplying this 20 into 8, so 20 samples per second and 8 bits per sample, that will give me the idea that is nothing but the 160 bits per second, that is nothing but bit rate. So this is how the bit rate can be calculated, and this is how the resolution of the ADC can be calculated. So these are the figures. Now let's proceed for the next, that is nothing but the how to calculate the fundamental period for any sequence. So this is what one of the question paper, in the question paper one question was asked related to the fundamental period. If you just concentrate on this question, determine the fundamental period of the sinusoidal signals. So few signals were given and it was asked for 6 marks. So let's proceed for this type of question. So similar to this, there is one more question. Let me just take it. This is from Proakis itself. So in this particular equation, or rather the statement, we can easily find that determine which of the following sinusoids are periodic and compute their fundamental period. So if I want to justify that for this particular case, let's say cos 0.01 pi n, this is what the sinusoidal signal given. So it is obviously the discrete time signal and we need to obtain whether it is periodic or not. So for any signal to be periodic, as we know, f is equal to, let's assume, k by n. So where this k as well as n must be the integer type of value. So to get this value of k, if I just compare this cos 0.01 pi n to the cos omega n, so I can just find here that it is nothing but 2 pi f. So 2 pi f is equal to what? 0.01 pi n. So it is nothing but like this. So here the case is pi will be cancelled, so pi will be cancelled, and what is remain? F is equal to 0.01 n by 2. So after solving it, it will become like this. So it will be nothing but 1 upon 200. But just compare this f equal to 1 upon 200 with the case which is just mentioned over here. With this case, if you just compare it, you will find that here k is nothing but the value, that is 1. So k is 1, and what about the denominator part? N is nothing but 200. So from this we can easily guess that this 1 as well as 200, these are nothing but the integer values. So that is why this particular signal we can say periodic with np equal to 200, that is fundamental period as a 200. So whatever the denominator quantity, that is the non-fractional number or simply the integer number, that will denote the fundamental period of that discrete time signal. Same is applicable for the further parts. So here after simplification, getting pi will be cancelled, so it will be 1 by 7. So again it is periodic with np equal to 7, means the quantity which is nothing but at the denominator. But here again it is the periodic one, so quantity at the denominator is nothing but 2, so fundamental period will be 2. But for this case, that is for case D, you can just compare this. 3 is nothing but 2 pi f, so f will be 3 by 2 pi. That is why it is non-periodic, since the denominator is nothing but non-integer value, so it is in short fractional value. And for the final case 10, so fundamental period is 10. So this is all about how to find out the fundamental period for any discrete time signal. So thank you everyone, thank you very much.